Yeah, so it's our pleasure to have Anurag Anshu today to give us a talk. So Anurag did his PhD at CQT in Singapore, and then he's done postdocs at IQC in Waterloo, and now he's at UC Berkeley. So Anurag has already worked on quite a breadth of topics, and I mean, he's been extremely prolific. For example, he had 5 papers in the last QIP. So, you know, come on, Anurag, you know, save some slots for the rest of us. And so he's worked on, you know, communication complexity, information theory, and he's also worked quite in depth on area loss. And he's going to tell us about his most recent work on that today. Okay, Anurag, take it away.
Great. Thanks a lot, Troy, for the very kind introduction and for kind recommendations as well. I'll take that advice. It's great to be here. I'll be telling you about this recent result with Itai Arad and David Gossett, which is on archive now. It came quite in March, quite recently. And the title is an area law for 2D frustration-free spin systems. So there are a couple of technical terms over here. Sorry if you keep saying this, people are entering the Zoom. I mean, I don't know how to stop that. Maybe not yet. There are a couple of terms here. I'll tell you what spin systems are, what frustration free is, and so on. So let's just get started on that. The system of interest for our discussion will be these 2-dimensional spin systems that look something like you see in this picture. It's a cartoon version of what might be something more general, but let's let's go with this one. So imagine a 2D lattice which involves certain number of particles, let's say n times L number of particles, which are arranged in a square fashion, like a square lattice fashion. So these black dots are these particles, and we can think of them as qubits or spins of certain constant dimension. When we combine them together, they become a huge 2 to the NL dimensional vector space, and this can be pretty large. And given this system, there is an interaction between these particles, and this interaction is defined by what is known as a Hamiltonian, H. So this interaction is called local if the Hamiltonian can be written in a certain specific way. So here, for instance, one could possibly write this Hamiltonian as a sum over these local terms. And by that what I mean is that a certain term Hij acts in a very restricted manner. So for instance, this Hij, it acts only on the particles that you see in this yellow placket, for example. And it acts as identity everywhere else. So this is a certain local term. This is called a local interaction. And the local Hamiltonian is basically a sum over all these interactions. So these models are very popular in specifically in quantum matter physics and also in quantum complexity theory for various reasons, specifically because they are very good approximations to real interactions that happen in nature, and they have a lot of predictive power to describe real materials. So for this talk, I will make a few assumptions. So for instance, I'll assume that each interaction interactions don't get too strong at some places. So for example, each interaction Hij, it's a positive semi-definite matrix, but it's at most identity. It's not too strong. I could also put a constant C here if you wanted, but we can scale the Hamiltonian terms in a manner that its constant is 1. A quantity of very popular interest is the ground space, which I could call as pi ground, pi gr. And this ground space is the smallest, the eigenspace with smallest eigenvalue for H. So that's the ground space, and studying the properties of ground space, because it represents the phenomena at low temperature, is of a lot of interest in the community. Now, there is another assumption that can be made, which is also quite made very regularly, has been done for a long time, which is the frustration-free assumption. And what it means is that the Hamiltonian Hij has a property that for all I and j, the hij have the ground space as their zero eigenspace as well. So each hij could have more eigenspaces which has 0, but the ground space is included in that. So computer scientists could think of this as a satisfied instance of a constraint, a quantum constraint satisfaction problem which is satisfiable. That's an example of a frustration-free model. So that's for the frustration-free model, and there are other notions as well. So for example, the spectral gap of the Hamiltonian is the difference between the ground energy and the next excited energy. So that is known as the spectral gap of H. And this spectral gap usually plays a key role in lots of phenomena related to these Hamiltonians. And for this talk, what will be relevant is a notion which I'll call the local spectral gap, which is the spectral gap over certain regions of the lattice. So for instance, I will look at over sub-Hamiltonians, for example. So for instance, I could look at I would be basically looking at square regions on the lattice, look at the Hamiltonian defined on that square region, and the spectral gap of that will be taken into consideration, and the local gap will be the smallest spectral gap over all such square regions on the lattice. So we'll work with this seemingly stronger notion of spectral gap for this system. So any questions about this setting? Sorry for the bad handwriting, by the way.
So the local spectral gap is just maybe an intermediate step. It's not in the final result that you're claiming that you have 2D, right?
Oh, it will be used in the final result. Yeah, the local gap will be. So this result will depend on the local gap. So I'll state it.
Oh, okay. So you have a condition that Hamiltonian has its actual property, and then
yeah. So it has local gap on every square of the lattice. Yeah. So they'll come later. Yeah.
Okay. So you need a square local spectral gap. Okay.
Yeah. All right. So so that's for the setup and a bit of motivation for why these systems are interesting. Now, one of the central quantities for this talk would be that of entanglement entropy, and the entanglement entropy can be viewed in the following way. So let's look again at our square lattice, and here are again our particles or qubits. Given any quantum state psi on this 2D lattice, we can ask, how does the entropy of this state psi, which I believe many of you will be familiar with, but I can just write it down. It's the von Neumann entropy of this state. How does the von Neumann entropy of the state depend scale? So for instance, if I take my lattice and divide it into a region, divide this into a region A and certain complement region, and the boundary between the regions is what I call delta A, then I can ask, how does the entropy of this quantum state scale? So for most quantum states, in particular, if I took a quantum state at random, the entropy would scale as the number of particles inside the smaller region. Let's say A is the smaller region. So that's called the volume behavior of entanglement. And it is believed that if I have a gapped local Hamiltonian, not just frustration-free with a local gap, but rather a gapped Hamiltonian itself, then it is believed that which is why this area law conjecture, it is believed that the entropy is scaled as the length of the boundary of the grid. So this is known as area law conjecture, and essentially the conjecture, the main aim of the conjecture is to distinguish these ground states from random quantum states and to show that these ground states are somehow special. They have some special properties. And there's also, and this is part of a large set of belief about these ground states. One of them also being that the ground states can be efficiently represented in a certain way. So we'll talk about that briefly later. But for the purpose of this talk, this is our central focus, the area law conjecture. So the main result that I'll talk about is that the unique ground states, state of a locally gapped frustration-free Hamiltonian on a 2D, the picture that we've seen so far, satisfies an area law. in the following fashion. It's the area with some very tiny correction that goes to 0. So a few remarks. Well, I've already discussed what frustration free is and what local gap is. One remark is that unique ground state is not really necessary, but it's for convenience for this talk. And one can pay an additional factor of log the number of grounds, the span of the ground space, if we want to talk about non-unique ground space. And we cannot hope to do better than this. If the dimension of the ground space is too large, then one can have very entangled states. There are examples where this happens. So uniqueness is a convenient assumption, or think of it as some small degeneracy of ground space. And it also applies to rectangular regions that I showed, which I did not talk about. But for this, we'll need a slightly stronger local gap. We'll need local gap on square-shaped and L-shaped regions of the lattice. So if this happens, then we can also prove it for rectangles. There is a technical takeaway for, I guess, if someone is more interested from computer science or mathematical point of view, which is much of the result will be about optimal polynomial approximations in non-commuting variables. I'll talk about it quite a lot in the coming slides. So that's the main result, and yeah. Yeah, there's some constant.
What do you mean by the boundary is rectangle?
Oh, so sorry. What I mean is that if you were interested in, so I showed you this picture where I was looking at this vertical cut of the lattice into two parts, like this into left and right. But you can imagine, for example, I'm interested in a rectangular cut or a square cut.
Okay.
Yeah. Yeah.
Okay. So in the theorem statement, the partition is like just cut.
Yeah.
In the middle, right?
Yeah, exactly. This is the theorem statement. But one could be interested in more general cuts. Usually, if you have area law for rectangular cut, then you can also prove it for other things like a triangle, or by kind of filling up the triangle with rectangles and so on. But so usually rectangle suffices. It's more convenient to talk about the vertical cut.
Okay.
Mm-hmm. Cool. Any more questions?
But the local gap, you need a square and this L-shaped region. But the size of these things are independent of A, right? Or
the size of these things, yeah, it's for a constant. Essentially, it's not strictly constant. Basically, there exists a size not too large for which there should be locally gapped.
Okay.
But that could depend. I mean, it's sort of a circular thing. So if there was a sufficiently large region of this kind where the local gap was not true, then this would be a problem. But I'll talk about local gap towards the end, in more details.
Okay.
More discussion about that.
Okay, thanks.
Yeah, if there's interest, of course. All right, thanks for the questions. So that's the main result. Let me spend 2 to 3 slides just telling a bit more about area laws. This is a slightly dense slide, but hopefully we'll go through it easily. So a motivation for this comes like from this very old results of Bekenstein and Hawking, where they argued that a black hole's entropy scales as the area, not the volume. And a very nice discussion of this can be found in the survey by Isaac, Kramer, and Planio from 2010. So in one dimensions, there's really one could argue that there's a complete story, although one could, of course, there's much more to be done. But from a conceptual point of view, the picture is quite very, very nice right now. So the first result for gapped Hamiltonians in 1D was given by Hastings in a breakthrough work, which showed that the entanglement entropy scales as exponential of the 1 over gap in one-dimensional unique ground states. Soon for frustration-free systems, 5 years later, Arad Landa and Vazirani, they improved this dependence on gap to 1 over gap cubed. And I'll talk a lot about their methods in the coming slides. So I thought to mention this result. And then Arad, Kitaev, Landa, Vazirani, they 1 year later, they improved the general result to 1 over gap, essentially exponentially improving over Hastings' result. And it is believed that this is tight, but there are no examples yet. Independently, Brandau and Horodecki, gave a different proof of Hastings result by arguing that any state with correlation decay, exponential decay of correlation, satisfies an area law. And because correlation length usually is 1 over gap, so this result kind of reproduces Hastings work. Now, the nice thing about this whole business of area law in one dimension is that this leads to a proof that the ground states of gapped Hamiltonians can be written as matrix product states, things that look like this essentially. I won't go into the details of this, but for someone who already knows, this might be just to remind you of that. And it also helps a lot in explaining a lot of successful results about the success of DMRG and more. In particular, for example, there are rigorous results by let me just do it shortly, by Landau, Vidic, Vazirani from 2015, and more recently by Arad, Landau, Vidic, Vazirani by 2017. They gave rigorous algorithms for preparing 1D ground states, which run in polynomial time. So that's the story in 1D. It's quite well understood. I believe any of you would agree. But in 2D, things are much more interesting and a lot less understood there. So it's known in several prior works. It has been shown that the area law holds under several assumptions, which are not really related to spectral gap, but there are several nice assumptions that we would make and then prove area laws based on that. So, for example, it's known that if the Hamiltonian is such that the number of low energy eigenstates are not so many, then one can prove area law using that assumption. Essentially, via trying to approximate the ground state by a Gibbs state. Also, when you have a special system, for example, a spin half lattice with nearest neighbor interaction, then using Bravi's exact solution, these authors showed that area law also holds for these systems. Under some adiabatic assumptions on the Hamiltonian, again, area law is proved, and also under some specific heat assumptions by these authors. It turns out that the area law is false in very high dimensions, which was shown by this work. It will feature again in one of the future slides. And recently we showed that although area law is false in this high dimensional system, but something else holds, which talks about these ground states. So yeah, so this is a bit of background on 2D and beyond. How things work there. Now, sorry. So with this, I guess if I'm going to now describe the details of these results and the methods involved. So if there are any questions so far, I'm very happy to answer that. Okay, cool. So let me tell you about how does one go about bounding entanglement. To do this, one way that was started off in Hastings' work was to find an operator, let's call it K, that approximates the ground state in certain way. So given an operator K, I'm going to denote the Schmidt rank of this operator K as the smallest number D, such that I can write K as a product operator like this, some left and some operator on A and some operator on the complement of A. And Schmidt rank, which I'll denote by SR of K, will be the smallest number that achieves this thing. And the idea is well, quite simple to start with, that find a K which has very small Schmidt rank and that well approximates the ground state. So what kind of approximations you could have? Well, you could start with something like an L1 approximation. So you could try to find an operator K which approximates the ground state in L1 distance up to error epsilon. And if this could be done, if Schmidt rank of K was small, then one could use some continuity arguments to say that the entropy of this also should be small. Because if the Schmidt rank of K is small, then its entropy is small and so on. But it turns out that this is very hard to guarantee. It's a very special criteria. And true in some specific cases. So this is not, I guess, not a very general way to try to prove area laws. A better way is to try to find an L infinity approximation, which is of course easier than L1 approximation, but it itself is quite hard. So here the idea is to try to find an operator K which approximates the ground state in L infinity and with some smaller epsilon. So some examples of these operators would be, for example, the Gibbs operator, of course, not this operator, but some Taylor expands and truncates this Gibbs operator up to some high degree of polynomial, and that would be a good approximation to the ground state. Or one could take, for example, the Hamiltonian itself and raise this to some large power. So this operator as well is a good approximation to the ground state, because when h is 0 in the ground state, this is equal to the ground state, and when h is more than 0, this term becomes small. So these are some examples that one could think of in trying to find an operator k that approximates the ground state. So that's okay. Oh, sorry, I should not have shown this earlier. Yeah, okay. So again, just to summarize what I showed in the previous slide, the goal is to find this approximate ground state projector, which is also known as AGSP, which is an operator k with the property that k approximates the ground state in L infinity error up to error epsilon, something epsilon, and the Schmidt rank is some number, let's call it d. So let's look at this thing for a moment, and let's ask a simple question. Okay, would epsilon 1 over 10 and d 100 suffice, for example? So one would imagine, for example, that at certain constant error 1 over 10, getting a tiny Schmidt rank like 100 seems to be pretty good. I mean, one would kind of intuitively expect. Would this be enough to prove area laws? Turns out this is no, and that's what I should have not written earlier. So it turns out that there are this very interesting family of approximations which can certify very large entanglement. So here's where it comes from. It basically comes from the work of Arnov et al. that I showed you earlier from 2013, I think. And it shows that you can have, for example, the maximally entangled state on a very large, of very large dimension. I mean, I'm calling it infinity, but it's a very large dimension, such that there exists an operator k. Let me call this operator w for convenience, which approximates a very large EPR state very well. Some error 1 over 10, but the Schmidt rank of this operator is tiny, let's say 100. So there can be operators like this which work well for even very, very large amount of entanglement. So this regime is clearly not sufficient to try and prove area law. And for those who already know, this construction of W comes from quantum expanders, which many of you might have seen. So turns out that to prove area law, one has to really have a very fine play of these parameters d and epsilon. So this is a theorem that we'll be using, which is due to Araleno and Vazirani. It says that if we can find d and epsilon such that d epsilon is less than half, which this would not satisfy, if this can be shown, then the entropy, the entanglement entropy scales as twice log d. And to give an intuition, I guess if we choose epsilon to be 0, for example, then well, k would be equal to the ground state. And of course, the entropy would be log d. But also when epsilon is not 0, but a little bit above, also like 1 over 2d, some very small number, then as well something can be said about this. So that's roughly how, so basically the standard tool is to use this theorem and try to prove bounds on the entropy. So I hope this was not too fast, and happy to answer any questions about this. All right, so now, as I mentioned earlier, some good examples of this AGSPK were these polynomial approximations. And one example was, for example, this 1 minus h to the power a large power, which is well a polynomial, surprise, of the Hamiltonian. And the aim is to keep the degree as low as possible, because small degree roughly corresponds to low Schmidt rank. Simply because if the degree was small, then the number of terms that would affect the Schmidt rank would be small, and hence entanglement would be low. So it turns out that for reasons that I won't be able to explain here, this is not a good example of an AGSP to satisfy this condition that I showed you earlier, that d times epsilon is less than half. One has to use something better, And in fact, anything better than this operator would suffice. The best operator that's known for this purpose is the Chebyshev polynomial, which was used by these authors. In fact, they observed the importance of Chebyshev polynomial in this area. So let me spend some time trying to explain how do Chebyshev polynomials come in. So in this picture over here, I have drawn the spectrum of the Hamiltonian, which is in the horizontal direction. So here's the ground state, it's an energy 0. There's a gap, and then there's a lot of eigenstates, which could be many, many of them, all the way to the norm of the Hamiltonian, which is the largest eigenvalue. The blue picture over here shows the ground function, which essentially peaks at 0 and is 0 everywhere else. And if I fed the Hamiltonian in this ground function, f, I would get the ground state, because for the Hamiltonian, every other eigenstate would be 0, set to 0, except the ground state. So a natural question is to try to approximate this ground state by a low degree polynomial. And it is well known from approximation theory for about, I think, a couple of decades by now, probably, that the best approximation for this function, which preserves the ground state and it keeps certain interval low, is the Chebyshev polynomial, which looks probably like this green, but not quite. Most likely, I think this curve should not be like this. But g of h is a low degree polynomial of the Hamiltonian, and this is what is used in the proof of 1D area laws. Now, it turns out that trying to use this tool in 2 dimension does not work. So let me try to give an intuition for why that doesn't work. I guess I'll have to say a few things which I haven't described in details, but I'm happy to discuss those. So in 2 dimensions, one could try to apply the Chebyshev machinery and try to see if area law can be proved. So let's go back to our figure, which is a 2D lattice, and we have lots of these particles in the same arrangement. Here's our cut, and I'm looking at trying to prove an area law for this. Now, because I'm interested in entropy around the cut, it turns out that it's sufficient for me to look at a region around the cut, which is of a constant size, which I'll call the effective region, and try to find a polynomial approximation around this region in certain sense. So what I can look at is an AGSP K of low degree and certain epsilon, which by degree I mean low degree in this region, which tries to approximate the ground state. Now, it turns out that the Chebyshev polynomial, it achieves a constant error epsilon, which is 1 over 10. And the degree of this thing is roughly square root of the number of particles here, which is roughly the area. So this is similar phenomenon that also happens in Grover search and so on. And also, well, this might be very familiar to many people in quantum computing. Now it so happens that if you notice, having an error epsilon of 1 over 10 and degree roughly square root is too high, because the Schmidt rank, which you would expect, it scales as exponential of the degree. It's roughly of this form, and the reason why this is a bad approximation is because when the area is large, this is worse than having the approximation that you get for infinite amount of APR pairs, which achieves an error 1 over 10 and Schmidt rank of constant 100. So the Chebyshev polynomial doesn't even achieve the Schmidt rank that you would get for very highly entangled quantum states. So there's no way Chebyshev polynomial can help you prove an area law in 2 dimensions because it doesn't achieve the right parameter. So any questions about this? Okay, good. So the way one can try to get around this, and this is the main observation that the first observation that we have, which is that this objection that I shared here, that the Chebyshev polynomial has too high Schmidt rank given a constant error. This objection is fair, but this should also apply to trying to prove an area law for commuting Hamiltonians. So commuting Hamiltonians, which basically arise when each of the terms commute. One can also assume that these Hamiltonian terms are projectors, but that's not super necessary here. It turns out that for commuting Hamiltonian, area law holds in all dimensions, including 2D. And there's a very simple proof for that. And if I were to use the Chebyshev approach to try and prove an area law for commuting Hamiltonians, I would basically run into the same trouble, and I'd not be able to do it. So there has to be a good reason why this is not really a real problem. So it turns out that if we look closely at the commuting Hamiltonians, then we find that although at epsilon 1/10, the degree of the best polynomial is still what Chebyshev gives, which is the best approximation at this error. It turns out that when epsilon is 0, I can get away with a slightly larger degree, that is roughly the area of the Hamiltonian, area of the cut. And this clearly beats the very good EPR approximation. So if I had an EPR approximation, at this degree, I would get roughly an error of 1/10 to the power this thing by simply raising this approximation to a power of the area. So this approximation I would get with certain degree, the linear degree in area, but for commuting Hamiltonians, I can get a 0 error at this degree. So it's sort of a sign that if we followed the construction of this commuting Hamiltonian, we would get an intuition for how to beat the Chebyshev barrier. So there is in fact more to it, and it turns out that there is a super Chebyshev behavior that happens for commuting Hamiltonian. So it turns out that if you have a commuting Hamiltonian, then the spectrum of a commuting Hamiltonian is integer always. That is, if I plot the spectrum similar to the figure that I showed earlier, the spectrum only takes these discrete points, unlike a general non-commuting Hamiltonian, which can have a very dense spectrum. So for these discrete points, there's a well-known result from query complexity and even approximation theory, which says that one can go better than Chebyshev approximation. And roughly, this is a family of results that were proven in 1995 and 1999 by several authors, which is that to achieve an error epsilon, I can have a degree roughly square root of the boundary times log 1 over epsilon. To compare this with Chebyshev approximation, if I were to show you how that would look like, versus Chebyshev would get us square root of this thing times log 1 over epsilon outside. So this log 1 over epsilon being inside the square root is a good big advantage that could help beat this barrier of having very good approximations at constant degree, at linear degree. So this is a hint towards how one would try to approach the Ariel approach. So this is exactly what we do, and our main, I guess, the technical theorem is the following, which says that for a one-dimensional locally gapped frustration-free Hamiltonians, I'll clarify why it's 1D soon, we can actually get this behavior of this polynomial approximation, which was earlier only known for commuting case, which came, by the way, from this classical results in query complexity. So what we can show essentially is that if I've given the ground space of a one-dimensional frustration-free Hamiltonian, which looks like this, with a local gap constant, let's say, then there is a polynomial P, not of the Hamiltonian, but it's a multivariate polynomial of all these local terms of the Hamiltonian, such that P approximates the ground state with an error which scales as degree as d square over the number of particles. So just to write it here, if I set this equal to epsilon, or maybe in a different color, if I set this to be equal to epsilon, then d would be roughly root n log 1 over epsilon. Versus the Chebyshev, which would be achieving this factor, which for error epsilon would be root n log 1 over epsilon on the outside. So this difference, as I already hinted in the previous slide, which seems to be crucial for explaining why commuting case error holds, is also what we can obtain for 1D frustration-free Hamiltonians. So this is the result in one dimension. This is, I guess, the main technical result.
So Anurag,
yeah, sure.
Yeah. Oh, can I just make sure I understand? So are you saying that, like, you can actually prove the area law for commuting Hamiltonians in this fashion, using this square root d log 1 over epsilon?
Right. So for commuting Hamiltonians, one can actually use this approximation to get a proof of area law.
I see. Okay.
And that's actually easy. I mean, commuting Hamiltonian is already known in a different way.
Right.
But the point being that this is a way which is more instructive for non-commuting case.
Right. Okay.
And it can explain why this Chebyshev barrier, which we saw here, is not a barrier for commuting Hamiltonians at least. And for and this over here, what you can prove is that for any 1D Hamiltonian non-commuting, we can also get the same behavior.
Okay.
Yeah. So this is general, yeah, with a local gap essentially.
So just the square root makes the difference.
Yeah, exactly. Just getting this thing in the square root makes a lot of difference, right?
Can you explain the intuition why this square root speed up would like have consequence?
Yeah, let me explain that. So let's look at, for example, yeah, let me try to do this here. Yeah. So with this behavior, let's set epsilon to 2 to the minus 1000 n, or maybe let me do it even worse, like 2 to the minus some big number, 10 to the power 4 n or something. Roughly. So at this approximation, what I see is that my degree is roughly 100 times n. So what I'm seeing is that I can get this very fine approximation at a rather decent degree. And to give an intuition for why this seems to be helpful, let's look back again what the unbounded number of EPR would give. So for those EPRs, this range of parameters, like this very tiny error and very good degree, basically is able to beat this. So let me just show you over here. So if I were to set epsilon to be 1 over 2 to the minus 10 to the 4 n over here, my Schmidt rank would roughly scale as something like I guess 1 second, I'm trying to fix that. Degrees 100, right? Sorry. My log Schmidt rank would roughly scales as some large number, I mean 10 to the power 8 times n, roughly. So this is basically, what happens is that only at this very tiny error regime, we can find a proof that our approximation is better than what was already available for this unbounded entangled states. And that proof is what is crucial, that helps essentially. And if you were to compare this, it's a simple exercise, I guess. If I were to look at this approximation and raise it to a high power and compare to, basically, if I look at this expression, then I see that Schmidt rank roughly scales as log 1 over epsilon in this case, in the case of EPR testing. Whereas Schmidt rank here scales as root n with a log 1 over epsilon inside the square root. So there is an epsilon where which this wins over that log 1 over epsilon behavior. And that epsilon is very tiny, but that's good enough for area. So you could think of this as a verification of the intuition that indeed these ground states are not too entangled. So is that helpful by any sense?
I see. So it's like you just want d times epsilon to be less than a half, but I mean you have the freedom to choose what epsilon you want.
Yeah.
So here you're actually going to take epsilon like this exponentially small thing,
exactly.
And that's why the square root is really helping you.
Exactly.
That's
okay.
True.
That's true. Yeah. So that's probably a shorter way to say it. Like the Schmidt rank times epsilon should be less than half. If you're comfortable with that, then this is a pretty short way to kind of convince oneself that this works. Yeah. But I guess the moral intuition is that this is the regime where we start seeing a difference from what maximum entangled states could be approximated with. Yeah.
Right. Okay. Yeah. Thanks. Yeah.
No problem. So that's basically I guess the main technical reason to put this thing in this in epsilon. And by the way, so if this could be done more generally, like if this kind of scaling could be achieved more generally for any, if this could be achieved for the ground space of, let's say x dimensional Hamiltonian, then we'll see in the next slide that this is proven area law for x plus 1 dimension essentially. So that's in this slide, and that's the next technical contribution, which is basically to observe that to prove an area law in 2D, I have to construct essentially a polynomial approximation around the cut. That's what we do. I mean, it requires some more explanation. I guess it's pretty hard to do it right here. But essentially, the trick which goes back this idea of truncation essentially is the idea is to view the Hamiltonian along the cut as an effective 1D Hamiltonian. So this H was my original Hamiltonian. My new Hamiltonian is H prime, which is a sum over these column terms. And H prime is basically a truncated version of the Hamiltonian that was sitting on each row. So once we have that, we have an effective 1D Hamiltonian, and we can employ this construction. And thankfully, it works out for this kind of picture as well. And then we get to the proof of the 2D array law by having the optimal approximation in 1D along the cut, essentially. So a physical message, I guess, a physics message here would be the following, which is this is intuition that we have that locality is the reason why array law should hold, and locality is something which we have seen a lot in gapped systems. So one example is, well, the decay of correlation is a measure of locality, and from the proof of Brandau and Herdecke, we know that this implies an array law in 1D, but it's not known in 2D. It's not clear at all whether those proofs will work in 2D. But I guess the optimal polynomial approximation that we saw is another proof of locality. And I'll give an intuition for why one could view this optimal polynomial approximation as a view of locality. But I guess the main message is that this actually helps to prove a 2D array law in comparison to the usual notion of decay of correlation. So this is sort of a physics message to adapt a more general notion of locality around the cut, essentially. So I'm going to give intuition for this proof of the technical theorem that I showed you 2 slides back. And maybe I'll also give this intuition why this optimal polynomial approximation, sorry, if I didn't describe this clearly, this is the one that achieves log 1 or epsilon inside the square root. Why the optimal polynomial approximation should be viewed as a notion of locality. And morally, that's because that's what happens for the most simple ground states around, which is the product states, the classical Hamiltonian. It happens for those, and then essentially the fact that this also happens for general ground states shows that these general ground states and these bit strings are not any different. So it's sort of a way to see the living local. So yeah, so I'm going to spend 2 slides trying to give an intuition for how to prove that theorem, the main technical theorem. And for this, I'll take this very simple Hamiltonian. I'll look at a 1-dimensional system and define a Hamiltonian which is a sum over these terms where I have a 0 acting on the ith side. So ground state is this very simple classical string. It's all ones. So if I look at the computational basis, it's not very hard to convince oneself, maybe in 2-3 minutes, that essentially the ground state is an and. It's sort of an and function of this Hamiltonian roughly. If I view x1 to xn as if I were to put a variable on all these bits, then I'm basically computing the and function of this thing, because when all is 1, when all the bits are 1, that's when I'm getting the ground state. So we know how to get approximations to the and function via either Grover or Chebyshev or this super Chebyshev kind of behavior that I showed you in different ways using the integer values of this Hamiltonian spectrum. But here's a different way to do it. And this way is sort of a divide and conquer kind of approach. So what I'll do is that I'll write the and function on these n bits as a and of certain k bits, which I can choose, and of n over k, a composition of these 2 and functions. So basically divide my this thing into these parts, each of size n over k, n over k bits here. And what I can do is that I can approximate this inner and with a Chebyshev polynomial with a constant error of roughly degree root over n over k, and find a way to compose these approximations. And those tools are actually available in the theory of polynomial approximation, and those are known as robust polynomials by Scherstoff. So my polynomial will look like a robust polynomial of these Chebyshev approximations, Turns out it's not too hard to describe this construction. And if you'd like, I can talk about more about this after this talk, where we discuss more how this construction really works. But for now, like please take for granted that there is this way to take these approximations of these individual smaller ants and compose them in a rather clever way, which was first observed by Shostov, to get this nice polynomial. And this approximation is so nice that it achieves an error of exponentially small in the number of variables, the number of variables to the outer end. And the degree roughly scales as the degree of the Chebyshev times the number of outer end, that's k. This goes like root nk. And if you notice here, then this is basically equal to root n log 1 over epsilon. So that's the different way to get the optimal approximations to ant function. And this approach is what, in fact, also generalizes to the quantum case. Note that the previous construction, I think try.
Oh, yeah, I just, okay, so for the inner function, you're just taking a normal Chebyshev, it just gives you constant error?
Yeah,
and then,
constant,
yeah. And then for the outer, you're taking a better error approximation, or I don't see where the e to the minus k is coming from.
Right, so basically I'm taking these inner approximations, and to put them together, I'm basically taking the robust function, robust polynomial.
Right, but that just like preserves the error, right? It just doesn't, the error doesn't increase.
Oh no, that actually decreases the error exponentially. It makes the error e to the minus k.
Oh, it decreases the error.
Yeah.
Oh, okay.
And this is in fact, I mean, this does look amazing at the first sight, but I can give a proof of this like soon after this talk. And
okay.
It's pretty easy actually. It's very elegant. It's definitely extremely elegant. So we take the constant error and then we do that. So I guess the takeaway of this exercise was that the previous constructions used the fact that this classical Hamiltonian had integer spectrums. That was no way true in the non-commuting quantum case. But this is using just two ingredient. One is Chebyshev, that is there in the quantum case, and this composition, which by the way also thankfully generalized to the quantum case. So that's what is this slide about, which is the proof of the technical theorem, which is we take the ground space and we also decompose it into parts. We have to be more careful here because unlike the classical case, the ground states don't combine together so easily. So one has to take overlapping things like this. And the overlap is like roughly n over k. So let's say the number of terms is like, number is like 2k instead of k. The overlap is roughly n over k. And the error that comes is, with the degree stays as before that I showed you in the previous slide. The error is as before e to the minus k plus this additional error which comes because we try to combine these subspaces. And that roughly, that comes from what is known as the detectability lemma. For those who know, so I may not be able to go into the details of this, which was first discovered by Aharo. So via this, this is the overall error. This is still not good enough because this error kind of messes up this error. But then what we can do is that we can compose this recursively and do it many times, and that kind of helps to approach the main theorem. And this is the reason why we get this tiny correction that you showed of an area law, which was the boundary to 1 plus order 1 over root log the boundary. This happens because of this regression that one has to do, which I can go to see. So yeah, so that's the rough intuition for this thing. And I can, this is the end of the talk. So I can tell you a bit about open questions. First thing is, can you prove area law in 3D, which amounts from the current knowledge that we have, it amounts to finding this optimal, there's very good polynomial approximations in 2D lattice systems. And it turns out that the current methods provably break down here, and we have to think of something special, something new to prove 3D area law. And of course, I guess the biggest question left is to prove the frustrated area law here, which we are unable to do, and to remove the local gap assumption, which we believe is very well connected to this problem. So I believe this would just help here a lot. And finally, one very interesting question is that to try to find the Pep's representation of these ground states, given that one can prove an area law. With that, thanks for listening. Yeah, and that's the end of my talk.
Okay, thanks, Anurag, for the nice talk.